About a year ago, I posted this video, revealing to the world a multimeter like no other. Literally. Because there was only one of them. This is the HYDRAMeter. As far as I can tell, the first open source general purpose multimeter. It's got tons of features that I've always wanted, but also had some issues I wanted to resolve. A year of testing, scope creep, throwing things out and starting over, buying and building test setups, throwing out test setups, some book learning, and blowing up a lot of stuff later, and I still don't have another revision done. But it is close, and it's time to tell you all what's been going on, and get people hyped for when it is. Long story short, this meter exists because I've always wanted a customizable multimeter that does everything exactly the way I want. These are our absolute most basic tool as electrical engineers, and they're made of electronics. So I wanted to be able to customize and hot rod it, and let anyone else modify their own if they wanted. The first version was a one-off that had all these crazy features like a wireless display, isolated USB, this input module that can add even more functionality, this sort of trinary tree-style mode selection, a fuse block, and some more modular parts inside. It wasn't exactly ready for any kind of production, though, and in solving a lot of the problems with this, it ended up leading me down 10 different rabbit holes. So I'm making this new version more trimmed down to the core, the important parts, to finally get some of these out into the wild. Getting to this point has taken some effort. Getting some legit testing going has been a huge part of this. I could do some really basic checks with just another handheld meter and a power supply, but getting to the point where I really know the performance and trust the design takes a whole lot more work. There's been 3 main categories of testing and validation I've set up: DC accuracy, AC characterization, and safety. Safety has been the most fun and foreshadowed so far, so I'll start there. In the movies, when something electrical goes wrong, there's a little poof and your hair stands up. In the real world, it's much less pretty. Injuries and deaths from arc flash are no joke. Multimeters are often right in the middle of this, and a poorly designed one can easily hurt or kill you. In the last video, I teased this capacitor bank. Yeah, that wasn't cutting it, so instead I've got this. This is a 1.6 kilojoule capacitor bank that can charge up to 8,000 volts. For reference, that's more energy than a typical 9mm bullet, and I'm dumping this into some little electronics parts. That's crazy. This is very roughly designed around the Cat 3 1000 volt standard for this kind of testing, though only in terms of peak voltage and available energy and source resistance. This won't validate if my designs actually meet the standard, but should give me a decent idea of what failures will look like and what my weakest links are. The schematic for this has only 6 parts, and every one of them ended up being a challenge. First was getting these big high voltage caps. I looked all over the place for anything that would work and not cost me a few $1,000s, even making my own polymer film capacitors with some plastic tablecloths and tinfoil. But eventually some really nice ones turned up for a reasonable price on eBay. I thought just finding these would be the hard part. I was wrong. That solved, the next challenge was how to switch them. I picked up this huge BJT that is rated for hundreds of amps continuous and can take a lot more peak. Yeah, that wasn't even close. It blew out instantly. I got an SCR that's rated for 2,000 amps for 10 milliseconds, and SCRs are pretty robust. Can take many times their rating for short bursts. This also wasn't even close, and also blew out on the first shot. I got really lucky at a swap meet and found more enormous SCRs rated for over 2,000 volts and 2,000 amps continuous, but even these blew out. Just these 2 caps have a pretty serious body count at this point. With this, I gave up completely on solid-state switching, and after a brief detour trying out a triggered arc, I used this car door lock motor to build a big steel mechanical switch. This finally did work. A good reminder to myself that sometimes, when it's not the point of the project, you have to stop trying to do the cool engineering thing and solve the problem with brute force and move on. Same lesson applied to the next part, the inline resistor. I didn't record this, but my first attempt at making this was to parallel a bunch of old 20 ohm 5 watt ceramic resistors I had lying around. Good thing I was wearing earplugs for this test because I discovered these can not just burn out, but detonate from enough energy. This was the start of one of my big lessons from this project as a whole. For a lot of fast events with a lot of energy, the effect is mostly just a factor of how much energy goes into the system. whether that's in the form of voltage, current, mechanical, or thermal energy, is less important than the total number. Dumping over a kilojoule into some little resistors like this, where the actual resistance element is relatively tiny, is just gonna pop them no matter what. So I went bigger, and bigger, and bigger, and eventually landed at this. Wow. Getting this working was a setback, but did give me some intuition for the forces I'm dealing with here. The charging circuit was probably the simplest, but still had problems. At first I used one of these little modules, from when I was planning to use this little doorknob cap, but that took forever to charge and ended up frying itself in short order. I picked up a neon sign transformer, but that had some issues of its own, and then turned in its resignation shortly after. That also fried the charging resistors and diodes in the process, so I had to beef that up with some high voltage parts. Stuffed all of that into a little PVC pipe for some isolation, and that's given me the least trouble of anything so far. Eventually I settled on this little module. It worked well enough, and then got a second one to speed up charging. There's little point in shocking these things if I don't know what happens electronically, so I need to take some measurements too, but at 8 kilovolts and a couple thousand amps, these aren't exactly common things either. For voltage, I started off by making a little differential probe. This was when I was planning to use the neon transformer, so I'd have to worry about grounding. So, need a fully differential measurement. This was a fun little side project, and leads me into the sponsor of this video, and project as a whole, PCBWay. Surely you've heard of them by now. If not, they're a very fast, low-cost PCB manufacturing service. They also do sheet metal, CNC, and 3D printing. I've been using them on my own and occasionally at work for prototypes for years now, and have always been pleasantly surprised with their service and quality for the price. While the PCBs were nice, this differential probe was like 4 diversions deep off the main project, so when some problems did come up, I just moved on and took the easy solution, which was to extend the voltage range of my 100-to-1 probe with a couple high voltage resistors and capacitors. By this point, I'd moved on to these little 12-volt charging modules, so I just ran the charger on battery power and didn't have to worry too much about grounding. Finally, there was the current measurement. That was even simpler, though I did my best to make it unnecessarily complicated. I started by trying to make a isolated high-speed current transformer, and that kind of worked, but I had problems with saturation and voltage coupling and just calibrating the thing. And for calibration, I got a big high-power 0.1 ohm resistor to calibrate with, and then quickly realized that resistor already does exactly what I need it to do, so current sensor. Check. Eventually, after cleaning the shrapnel out of my carpet enough times, I decided to get some kind of box to hold everything during testing. I started with just this cheap cooler and a piece of acrylic taped on top, but for my talk at Hackaday SuperCon, I wanted to do one of these tests live on stage, and figured that injuring audience members with shrapnel or damaging their hearing was a bad idea. So, I made this nice sturdy box with a couple layers of polycarbonate to contain everything and keep the noise to a manageable level. This worked really well, and my neighbors are probably thankful. And having got all of that working, I can finally blow things up in a controlled way with useful feedback. The biggest thing I learned from this is what I said a second ago about energy. Our main goal in all of these circuits is to minimize the energy going into these parts. Withstanding the voltage is a big challenge in achieving that. If something breaks down and either fails short or arcs, a lot of power gets dumped into that arc and everything pops. The most power transfers between two circuits when their input and output resistance match. Since I wanted to minimize the energy going into the meter, that means having it as far from 2 ohms as possible. Interestingly, and a little counterintuitively, going either higher or lower works to minimize energy transfer. Problem is, an arc will end up somewhere in that neighborhood, which means massive power transfer, which means boom. So, arcs are very bad. For voltage and resistance modes, I'm going high impedance. The normal input resistance is 10 mega ohms, but for various reasons we want an input resistance around 1000 ohms. Link to some more details here. In testing, I found 2 very specifically chosen resistors in series were enough to handle this. Like most of us, they do burn out when overstressed like this, but they don't cause too much fuss in the process, as long as the current stays low, so the resistance stays high, so disaster averted. A varistor to ground after the resistors limits the voltage going to the other components. For current, we go low resistance, so the meter will have to handle thousands of amps for a few microseconds, but the voltage stays fairly low, so power stays fairly low. This huge current blows the fuse almost instantly, and that is designed specifically to disconnect high voltage at high current without exploding. A couple basic diodes are enough to keep the effective resistance of the meter low. They'll tolerate enormous current for a few microseconds, and that's all we need. If you want more details on how all this works, I did a really detailed breakdown of all the circuitry. Check out the video here. So I got this ancient 5.5 digit meter at a swap meet, and this programmable high voltage power supply. These made for a step change in my ability to test this for DC. I whipped up some little GPIB adapters. Shout out to Twilight Logic's AR488 project. With that, I was able to slap these together in like half an hour and for like $4 instead of the absolutely insane prices they charge online, and they work great. These let me computer control the supply and meter so I can run a fully automatic voltage sweep and correlate against this reference meter. But how good is this meter now? Looks like it was last calibrated like 15 years ago. Well, I've got access to a calibrated 6.5 digit meter at work, and I brought this in after hours. Figured I'd spend a very late night on yet another side project figuring out how to access the calibration settings, having to set up and run a whole bunch of tests and code and reload the new calibration to the thing, and oh, it's still accurate to the last digit. Wow, HP knew what they were doing back in the day. Presumably they do now at Keysight too, but I can't afford anything made this millennia. Well, that's one side project I can skip. What was I supposed to be doing again? So I made up these test boards for the new inverting front-end configuration. New analog switches, 24-bit ADC, and a couple other changes. Again, shouts to PCBWay for making these. With this and the programmable supply and meter, I can do a full characterization and calibration of the voltage front end. That's pretty great. Check this video for the only real problem that emerged there. There was one minor hitch, but otherwise it works well, and I was able to resolve that problem by just running the op amps on a 5-volt supply instead of 3.3 volts. I put less work into AC characterization. I got a pretty cheap oscilloscope with a function generator, and wrote some terrible Python code to input some voltage at various frequencies and measure what comes out the other end, both analog and from the ADC. There wasn't a ton to see here. While this took a surprisingly long time and a good amount of effort, it only really confirmed that the simulations of basic resistors, capacitors, and op amps work. This did validate that my models were reasonably accurate and the circuit itself was reasonably well behaved, which is good. But upshot is that this has a pretty flat response up to a couple of kilohertz and a decent drop-off after that. We of course want a flat response at low frequencies to make accurate AC measurements, but the drop-off as we go higher isn't really about preventing aliasing in the ADC. This is not meant to be a spectrum analyzer. Instead, it's more about high-frequency noise coupling in. Long leads will pick up a lot of noise, down into the tens and hundreds of kilohertz, and that noise was a substantial problem in the first version. So, with all of that, it had been a while since I'd actually done much design work on the meter itself, and around December I finally decided, I've done my homework, it's time to get another version of this out there already. I want to be able to make more than just a couple of these. The first version was everything I wanted, but for this version I wanted to trim some of the fat, do some DFM, price out parts, and maybe make a dozen or so so I can send these out to other people to test and play with. More of a proper tool than just a fun project for myself. It might be a little presumptuous, but I like to think that especially in this day and age of disposable, proprietary, black box designs, that any open source repairable project is important. I want this to be out there in the world and being used, and not just on my bench. I had to check some of my engineering pride on the less necessary elements, and took the simple solution to a few of the problems that came up. It's not perfect, but I can either make every little part of this perfect, or I can finish it within my lifetime and for less than $50,000. It's a strict either or. It feels a little weird that I'm slightly unhappy with every single part of this project, but also really happy with how the whole of it's turning out. Often it feels like that's one of the essences of engineering, getting everything good enough and moving on to get the job done, even though it could be just that little bit better. Top level, the biggest challenge here is probably supporting a rotary switch. The front end had to change quite a bit to make that work, but I'm fairly happy with how all that worked out. I'm using a common 2-pole 6-throw switch, which took some real work to get all the functionality in so few contacts, but did work out in the end. One pole connects to the voltage jack and switches AC and DC voltage, resistance, and a dedicated millivolt mode. A normal meter will usually reuse the millivolt input for resistance, but I can't do that with this switch, so I have to have 2 separate millivolt front ends, which seems like an okay trade-off to me. The other pole of the switch both has to switch milli and microamps and tell the microcontroller what setting we're switched to. This was tougher, and I went through a couple designs, but ended up on this one. To do the milli and microamp switching, I needed to set up the shunt resistors for those ranges like this. Normally we're in microamp mode, but when we switch to milliamps, this closes and all the current goes through this shunt. Problem is, now the common terminal of the switch is at the common potential, which for various reasons, see here, is 1.65 volts above my digital ground. Because the resistance goes from about 100 ohms to just under 1 ohm, without putting a bunch of current through it, which would mess with my current readings, I can't think of a way to easily tell if the switch is in this position. But I can deduce the position by measuring all the others. If these are connected to common, we're in that range. If they're all floating, then we're in milliamp mode. Problem is, any current that flows to measure this, like with a pull-up resistor, will go through the microamp shunt and mess with my microamp readings. I went through a couple solutions, but ended up on this one. Turns out the reverse leakage of a common 3904 BJT emitter diode is like crazy low, easily sub-nanoamps, below a couple volts. So I figured out a setup where a shift register reverse biases the emitters normally, so that only that tiny leakage makes it into the microamp measurements. So far so good. Then, in between microamp readings, I can pull the emitters down one at a time, and if the switch is in that position, then the base will be pulled up to common, so base current will flow, so the collector will pull down, and I can read that into my microcontroller, and to know that this range is on. If it's high impedance, the BJT won't turn on, and this line will stay high, and I know that this range is off. This seems pretty simple and obvious in retrospect, but it took me a lot of iterations, turning the problem over in my head, redesigning everything from a system level to avoid this problem entirely, and complete redesigns to arrive here, and this is just like one tiny piece of this project. This project doesn't have that many parts, but what is here is easily the most I've thought about, analyzed, and iterated on any piece of circuitry I've ever made. It's pretty satisfying, really, to see the little improvements with every iteration and understand something like this at this level. It's also one of the things I love about open source, is that other people can then draw from this and make it even better, or apply aspects to a completely unrelated project. So many little pieces of ideas and nuggets of wisdom have come from other projects other people have shared. It'd be impossible to list them all, here's just a few that I can think of. Which is also my encouragement to share your projects and what you've learned. Even if it's incomplete or you don't feel like it's that impressive, just putting the information out there means someone else can build off of it, and you'll never know what can snowball from that. Rounding out the top level design, we've got some soft keys to select more advanced modes, a graphical display, the isolated USB port, and some nice shielded front panel jacks. Fuses I kept as 1/4 by 1 1/4 inch ceramics instead of the huge fiberglass reinforced ones for serious Cat 3 or Cat 4 meters. These shouldn't be used for anything serious, and $10 a pop for the big fuses is excessive if they aren't needed. Power is kept simple with a 9-volt battery, though I do want an option to go rechargeable in the future. What's left to do is finish layout. Depending on when this video is out, that may or may not be completed. As I record this, I've got all connections made, but still have some cleanup to do. Selecting specific parts for everything and sending them out for fabrication comes next. I'm going to make a dozen or so of these, depends on pricing, and I've got to design the cases entirely, which I'll be doing in FreeCAD. It's great that at this point we've got fully open source tools for everything, from the software to the electronics to the mechanical hardware. If you want to support this project, something as small as subscribing and turning on notifications is great. Let the algorithm know to show this to more people so I can get more and bigger sponsorships to accelerate this. Put in your email to the form in the description for updates, mainly when pre-orders or crowdfunding is available, and I've also set up a Discord and a Buy Me a Coffee, both linked below. I'll be opening up the current state of the design for commentary and improvement on the Discord, and the Buy Me a Coffee is straight support for the project. I don't have any direct incentives yet, but once I do, I'll make sure they're retroactive, so anything given now will count towards that. Thanks for watching and supporting the project. Happy testing.